opening presentation about assessment of the physical requirements to global phase out fossil fuels. And presentations our Simon Peter Michaux, Associated Professor, Metallurgy, Geological Survey of Finland. And Simon is a very, very high specialist about circular economy, about mineral resources, mineral processes and mineral resources. So, Simon, you have floor, please.
All right, hello everyone. So I'm going to present a summary of two pieces of work that have been published recently by GTK. This is going to be the assessment of the physical requirements to globally phase out fossil fuels. Before we get into that work, I'm going to show you some data and information about what the renewable energy system is trying to replace. First of all, here is the metal price for the metals that the World Bank uses to track the health of the industrial ecosystem. This is the metal prices for aluminium, steel, copper, lead, etc., but also for precious metals and for energy resources, oil, gas, and coal. So what I've done is I've overlaid these numbers and I've indexed these numbers to the number 100 and the month of December 2000. And what I've done here is to overlay these metal prices to show periods of relative stability. And as you can see, prior to 2005, things were reasonably stable, with the exception of the 1979 oil crisis. But in early January 2005, this happened. So a structural volatility in the metals price hit the market, and the largest economic correction since the 1929 Great Depression was not enough to resolve whatever structure that was. Now, metal price is the handover point between those who extract and produce the metals and those who use those metals to make useful things. So a case can be made that this blowout was a chain reaction that started in the oil industry. I can make the case, for example, that the global financial crisis actually started in the oil industry 3 years earlier. So the major economic correction did not resolve it, which means it's not a speculation problem, it's a structural problem. And the change started something like 17 years in our past. So this is to show the industrial ecosystem is evolving now, as in it's not something that might happen in the future, it's happening now and it's already started. So what happened? In 2005, oil production. Oil is the primary resource. It is the heart of our industrial ecosystem at the moment. In 2005, in January, it plateaued. So it was oil traditionally has expanded with population growth, but in 2005, it could not increase. Saudi Arabia at the time was the swing producer, and they were able to regulate price, supply and demand by just increasing production and decreasing. At that time, when they were required to increase production, they were not able to do so, even if they increased their rig count. They had a 146% increase in rig count in exchange for a 4% decrease in oil production. So supply and demand separated. So there's the same points there. So here is oil supply and demand. And here's oil price correlated to the same point on the graph. And for a short period of time, production plateaued. And within that window, supply and demand separated, and that facilitated an oil price spike. Now, at the peak of that, the oil price got to a peak and then it crashed. That peak correlates with the start of the global financial crisis. We fixed that global financial crisis with quantitative easing, or printing of money. And so the system is now held together with the printing of US dollars and other currencies. At the same time, an innovation in the horizontal drilling industry of tight oil was able to facilitate the fracking oil industry in the United States, and they became the swing producers. So a case can be made that the GFC was caused by a chain reaction that had its genesis in the oil industry. Quantitative easing resolved the crash. We're living on a credit card. And so fracking our tight oil was able to make up the supply shortfall. And the United States is now the global industry swing producer, with the majority of growth coming from the tight oil sector. So let's look at oil. I saw this chart for the first time as an undergraduate geologist in 1992. I did not understand what it meant at the time. So here is all the oil discoveries going back to 1930. You may notice that most of the oil has been discovered in the 1960s. Inside this little red square in the bottom right-hand corner is a study released by Rystad. So there's a record low of discoveries in 2020. The largest oil deposit of all was discovered in Saudi Arabia, and it was the Gawa deposit. Remember that because we'll come back to it. 81% of existing producing fields are in decline, and they're declining at an average of 5 to 7% per annum. Of the largest 10 producing fields, the youngest was discovered in 1976. Here is that same data, but now produced in a cumulative percent form. The purple is the purple is discovery, sorry, and the green is production. Half of all oil has been produced since 1994. There's been a net decrease from stocks and reserves since 1981. That point there is that point. 1981 is actually on a chart on the right. Our energy use has increased steadily. We are not slowing down. Now, once energy becomes much more expensive, the economics of all other raw materials will change. And all raw materials, I believe, will have this profile eventually in some form. So oil production, oil consumption is a proxy for economic development. What would happen if the entire world became as developed as Germany? So 2018 is the column on the left. This is the amount of oil we consumed. And the charts on the right, the middle one is the BRICS economies consumed per capita the same amount of oil as Europe did in 2018. Look at India. India has expanded enormously. And the column on the far right is if the entire world consumed the same amount of energy per capita. All developing economies want to be the same as Germany. So BRIC economies increased by 254%, the rest of the world by 71%. The United States would have to shrink. We will need an extra 117 million barrels a day to achieve this. Or if Saudi Arabia Gawa field produced 3.8 million barrels a day, we would need to discover and then develop 31 new Gawa deposits. So this means that the technological inequality that we see in the world at the moment cannot be resolved. We cannot resolve this with the oil industry. So here's oil and consumption production for the last couple of years. Peak oil at the moment is November 2018. It's in our past. So just after that, 9 out of 10 tight oil producers had cash negative negative profile in the United States. They've since resolved that. They're not cash negative anymore, but there's not enough cash to do the aggressive drilling to keep fracking going. And then there was the COVID-19 quarantine lockdowns, which is the gift that keeps on giving. But in that time, for the previous 12 months, demand has actually exceeded supply. So the oil industry is in trouble. And that brings us to this work, which I'm going to present to you today. This was the assessment of what would be required to phase out fossil fuels. What's the mechanics? So what did I do here? I've worked out the physical tasks done industrially by fossil fuels, and determined the true scope of the useful work done, with the idea that each energy source has an efficiency level. I then assembled what was available on the market, all the non-fossil fuel systems that could do useful work, and I calculated the quantity of electrical power needed if I summed all units together. I then assumed that if we had the same energy mix for the non-fossil fuel systems in 2018, if I expanded that to the new capacity, how many new power stations would be needed and what kind? In this report, we have the number of vehicles by class, the number and size of batteries, an understanding of when you'd use an electric vehicle and when you'd use a hydrogen fuel cell. I did an estimate of the rail transport and the maritime shipping transport fleet if they were electric versus if they were hydrogen. Estimates to phase out fossil fuel industrial applications like power generation. Examination of the feasibility of expanding the nuclear power plant fleet. Can nuclear save us? I also examined the scale-up potential for biofuels, and the plastics and fertilizer industry was looked at. So this all started with a conversation with my management. They wanted to know how many minerals, how much minerals and what kind of minerals be required to resource the gigafactories of Europe. So it started with, well, what metals will we need of the different systems? And then I worked my way backwards back to exploration. And that was the original plan. But it became apparent that certain things are missing. And so I went and filled in the missing gaps. So how many vehicles are we talking about? And what do they do? What physical tasks? What distance do they travel? If everything was a hydrogen fuel cell, what would that look like? And so on and so forth. And that gave us the amount of metals, but it also gave us the amount of power that will have to come off the grid. And so that told us the number of solar panels and wind turbines. And along the way, we'd have to work out what industry needed according to the 2018 system. So what I did was, instead of actually trying to predict what will happen in 5 years' time or 10 years' time, I decided to do the following. We will see a ramp up of non-fossil fuel systems to come in and replace the existing systems. We're going to install wind turbines and solar panels and as fast as humanly possible. But there'll come a point when the existing system is replaced. When you travel through your city of Tallinn, the cars you see driving around you will all be non-fossil fuel at that point. So it'll be some point in our future. After that, then we'll sort of settle into a more stable growth pattern. So I want to look at that point there. How do we replace the existing system, like full replacement? All the cars, all the trucks, all the aircraft, all the maritime shipping, how much power will they need? Where will we get that power from? So what do fossil fuels do for us now? How much electrical power is required to phase out those systems? How many cars and trucks? And so on. And at the bottom of all of this is what quantity of minerals will be needed to do this. Calculation arc went something as follows. We assessed the true scope of tasks to phase out fossil fuels as a complete replacement with non-fossil fuel power systems. So I looked at the existing transport fleet size, cars and trucks, rail, maritime shipping and aviation. I did this for the United States, Europe, China, and the fourth calculation was the globe as a global system. And what I'm showing you today is the global calculation. So that gave us the number of technological units we will need and an estimate of the proportional mix. And to put this in context, in 2018, 84.5% of the global primary energy consumption was fossil fuel based. So most of the system has yet to actually be constructed. So also there was the number of power stations, but also the amount of buffer power storage to manage intermittent supply from wind and solar was looked at. If you couldn't be bothered reading the report, which is rather large, sorry about that, but read this black box. Current plans are not large enough in scope. The task before us is much larger than current paradigm and planning allows for. Base calculation went something like this. The global fleet of vehicles was something like 1.4 billion. Now, that is a conservative estimate. The real number could be 1.5. Those vehicles traveled an estimated 15.87 trillion kilometers. Put this in context, less than 1% of vehicles in 2020 was electric vehicle. So the vast majority of these vehicles will have to be built from scratch. And as they've been built from scratch, they cannot be recycled. So it has to come from mining. Now, because I compared electric vehicles to hydrogen directly, I was able to do some interesting things. So an electric vehicle battery for the same parallel system was 3.2 times the mass of the hydrogen cell fuel tank that would do the same tasks. So that meant for the same energy storage, a hydrogen fuel cell could go 3.2 times further or operate 3.2 times longer. Meanwhile, to manufacture that hydrogen, we required 2.5 times the electricity compared to charge the equivalent battery. So you put those two things together, all short-range vehicles should be electric vehicle systems. So all passenger cars, commercial vans, delivery trucks, anything that stays within a city range and within a 100-kilometre radius should be electric vehicle. So we're talking about 65.2 terawatt hours of batteries. Now, all of the studies I've seen talk in terms of gigawatt hours of batteries. This is terawatt. All long-range distant vehicles or heavy vehicles should be hydrogen fuel cells. So all Class 8 HCV semi-trailer trucks, all rail that is not electric so far, for example, freight, and all the entire maritime shipping fleet should be hydrogen. That's not to say they can't be electric. It's just it's more efficient if everything is hydrogen. We will need 200 million tons of hydrogen annually. So let's put the system together. So here is the electric vehicles. Those vehicles travel that distance, and we will need that amount of power to charge those batteries. This is the amount of power we will require to phase out gas and coal electrical power generation, building heating, and steel manufacture using coal. And here's the hydrogen system. Those vehicles travel that distance and they will need that amount of hydrogen. And if we were to use electrolysis, like green hydrogen, we will need that amount of power because we're not allowed to use gas to make hydrogen. I looked at biofuels, and biofuels may be the sensible way to keep the aviation industry going. It also could be the only way to keep the plastics industry going, and it also may be the best source for our fertilizers. But it is not clear how much we can actually sort of extract out of the environment and be sustainable. So it's recommended a full sustainable audit is required with these metrics in mind. So let's put the power systems together. This is the power we need. We will need an additional 36,007.9 terawatt hours a year. Now, to do that, we're talking about over 200,000 new non-fossil fuel power stations. To put this in context, the power plant fleet in 2018 was 46,000 stations. This shows the difference in energy return and energy invested for the individual for non-fossil fuel systems compared to fossil fuel systems. So if we put that all together in the energy split that actually happened in 2018 and expanded it accordingly, this is how many power stations we will need. Now, the elephant in the room is the stationary storage. Wind and solar are highly intermittent. We need a buffer. Now, supply and demand for the energy system has to match. And as demand goes up and down, supply has to go up and down. At the same time, wind and solar are highly intermittent, both on a day-to-day basis, but also on a seasonal basis. So we need a buffer. And in the literature, that buffer is recommended. Some of them, authors are recommending 12 weeks for the entire system as a buffer, or 1 month for the entire system. I'm recommending a 4-week buffer for just wind and solar only and nothing else. Now, if we were to do that, we need 548 terawatt hours of batteries. That is almost 10 times what we need for electric vehicles. Now, currently, to protect the system, we are using the gas industry as that buffer. If we take the gas industry away, we need to find another buffer. And at the moment, coal can't do it, nuclear can't do it. So without gas, we're in trouble. So if we were to deliver 1,000 terawatts of power to the grid over 1 year, I ran some statistics of the performance of power station systems in 2018. Nuclear was our best performer by far. But there's wind and solar. Now, the International Energy Agency believes that the future is going to be based on wind and solar. But if we were to do that, let's say you want to deliver 1,000 terawatts of power a year. How many stations would we need? Well, you could knock out 147 coal-fired power stations, but you'd need something like 30,000 solar PV stations to replace them of average size. That's not solar panels, it's stations, solar panel arrays. So renewables have a much lower energy return on energy invested ratio than other fossil fuels, and they may not be strong enough to power the next industrial era. So here's those numbers graphically. This is the non-fossil fuel power systems that we can use at the moment. The white, oil, gas, and coal, is what we want to phase out and replace. The green on the right is what we need to bring in and replace. So the tasks are as follows. Yeah, to put this in context, in 2018, we produced globally 26,614 terawatt hours of electrical power for the year. So we are discussing making a power grid that is larger than the existing power grid with expensive and complex power that's not as flexible. That's the nature of the task in front of us. So charge the batteries, make the hydrogen, phase out oil, gas, and coal, electrical power generation, heating of buildings, and the little sliver on the top is the coal industry. So that's the next generation of work, which I will now show, is the International Energy Agency has actually released an estimate of what they think the energy split of 2050 might be. And so I've taken this sort of column on the far right-hand side, and I've imported that into my work. So this is the task. This is what we need to deliver in an additional capacity. So how do we split that up to the new energy split? And so I've come up with these numbers. So I've assumed the following: the nuclear power plant, capacity will double in size, 100% addition. Hydroelectricity will increase by 120%. So the remaining power will come from, geothermal will triple in size. Bioenergy to waste will stay the same because we can't harvest too much more from the environment anyway. So the remaining power will come from wind and solar, 50% between each other. The wind will be split between 70% onshore and 30% offshore. The solar will be split to 90% for photovoltaic and 10% for thermal. So I took those numbers and I worked out how much extra capacity we will require, and then that gives us the estimated number of new power stations accordingly that we will need. This is the new energy split. So this was developed from a combination of the IEA 2021 projection and some of my own assumptions from my own work put together. So gas and hydro are the existing buffer. Generation and demand must match. So here is a snapshot of a Canadian power system for a period of time. The orange is nuclear. It doesn't really change much. It's your base load. Coal behaves the same way. So then you've got hydro in the pale blue. Now, hydro can go up and down to match supply and demand, but it has a relatively narrow window of action. Gas, on the other hand, has enormous variation. Gas can be turned on and off at will, and without damaging any power plants. That is not the case with other systems. So we need something to replace gas if we're going to use wind and solar. In fact, if we take gas out, the balance between supply and demand remains the same, and so we have a problem if gas is removed. So solar. Here is the solar radiance on a daily basis in Germany. And as you can see, in summer, we get much more sun than in winter. This is what happens in the Northern Hemisphere. So it also means that solar is simply less effective in winter. And in winter, especially in places like Finland, solar panels tend to get covered in snow for long periods of time. Wind is also highly intermittent, and it varies between the seasons as well. And you can have regional variations that go for days and then sometimes weeks. So this is how I came to the idea of, well, we need 4 weeks buffer storage. That's conservative, and a strong case can be made that is too conservative. So, stationary buffer storage. If we would use the energy split I said before, where we were talking about 34% for solar PV and 36% for wind, that will require 548 terawatt hours of buffer storage. This is the elephant in the room. I have not really seen this discussed effectively in the European Commission planning meetings at all. It's aware that they do need buffer storage, but it's not clear how much. In Australia, there is a 100 megawatt, 129 megawatt hour power station that is lithium-ion based, that is providing a buffer for the local wind turbine array, and it's been quite successful. So if we were to say we're going to make, how many of those stations will we need? In the global system, we will need 15.6 million power stations like that, if we were to go down that route. Okay, so we've assembled how much power we need and how many systems we need. So now let's look at the metals. So the IEA released a nice report that showed the metal content for the different systems. And so I was able to go through each and every one of these systems and estimate the metal content. So the market, they also had a projection for in 2040 what the market share would be for, say, wind. So I used the 2040 numbers. And so we had 4 different technologies for wind turbine, and we had estimations of what they would be for onshore and offshore. And then they had the metal content for each of those wind turbine technologies. So I was able to estimate the amount of metal that we will need for the global wind turbine fleet. So solar panels, same thing. They had an estimate of what the actual market would be in 2040. Now, most of the market, 90% of the market seems to be crystalline silicon. And so I was able to find a metal content estimation for crystalline silicon solar panels. I wasn't able to do that for the thin film solar system, so I've assumed that all new solar panels will be crystalline silica. In different battery chemistries. So we've got an estimate of what's actually in each battery chemistry in terms of metal content. And we've also got for 2040 what the market will be for the different battery chemistries. This is for both electric vehicles and for stationary storage. So if we summed all that together, so first we've got the number of technology units. That's this slide here. How many cars, trucks, electric vehicles, hydrogen fuel cells, solar panels, wind turbines, etc. will we need? And this is everything. Electric vehicles, EV batteries, hydrogen fuel cells. This is the wish list to phase out fossil fuels to make 1 generation of units. Remember, each of these units, once they've been produced, will only last in between 8 and 20 years, and then they have to be replaced. So this is not a permanent addition. This is a 1 generation. So I think I summed together the metal needed across all the systems shown into one place. And then put these numbers. Okay, so what if we were to put those numbers against production? So I've assembled the metals that we've needed in the far left-hand side. Then you've got the total metal required to produce 1 generation of technology to phase out fossil fuels. And the numbers are huge. Then I've got the 2019 production rates. Now, 2019 was the last sensible year of data. After that, we had the corona pandemic lockdowns, and there are artifacts in the data. So 2019 could be the last sensible year of data for some time. So to estimate and model our system, 2019 will do. The final column is the number of years at 2019 production rates that we will need to produce the metals. And you may notice some of these years, in terms of years, are enormous. Thousands of years. It's not going to go well. So what we now need to do is open more mines. Now, we could say we don't really use lithium or cobalt or vanadium very much. So in theory, that's not a problem. So it's just a question of just tapping into our reserves. So I examined that amount of metal needed up against our reported global reserves from the USGS. Now, the second column from the right is the proportion of metals required to phase out fossil fuels, global reserves as a proportion of the metals required. And as you can see, existing reserves, as stated, are not only not enough, they're nowhere near enough. So to put this in context, for every 1,000 deposits we discover, only 1 or 2 become mines. And the time taken to develop a discovered deposit to go from to a producing mine is about 20 years. And for every 10 producing mines, 2 or 3 will lose money and shut down because they're not viable in that market at the time. So this is a big task. And at this point, it should be apparent that we should perhaps seriously rethink our plans of how we're going to do this and what our expectations are going to be. The final column is, if reserves are enough for 1 generation, how many generations of technology can we actually make from global reserves? And if we've got only, like, say, 6 or 7, it means global reserves, like geological reserves that were created in geological scales, are only good enough for about a century, after which society has to do something else. So what we're looking at is the stewardship of the planet Earth. So we used to have a small human system sitting on a really large natural resources with a small pollution waste stream. So we've got an industrial system, ecosystem of unprecedented size and complexity that took more than a century to build, with the support of the highest calorifically dense source of cheap energy the world has ever known, as oil, in abundant quantities with easily available credit and unlimited mineral resources. Now we've got a massive human system, a really depleted natural resource feedstock, and a massive pollution stream. So we now seek to build an even more complex system with very expensive energy, with a fragile finance system saturated in debt, not enough minerals, with an unprecedented number of human population embedded in a deteriorating environment. So current thinking doesn't quite understand the pickle we're in. So the World Economic Forum released a report in 2019 saying that, and the European Commission has committed that by 2030, 30% of the global fleet of vehicles will be electric. And they think they will need 10,000 terawatts to extra capacity in the grid to actually charge those batteries. So my numbers are to do the same thing, because with the understanding we're split between EV and hydrogen fuel cell, is 4,800 terawatts. So they substantially misunderstood the size of the problem. And the World Economic Forum report has misdiagnosed the size of the global fleet, and that's the problem. They also underestimated the amount of batteries they think they're going to be made by 2030. Remember, 2030 is only 8 years away. They think the World Economic Forum has projected they needed 2,623 gigawatt hours of batteries produced and running, whereas I'm projecting the same level of 30% is actually 19,556. So if we were to actually, how many power stations are we talking about? So what I've done here is there's 2 scenarios. There is the planned energy scenario. And this is actually the primary base case for the ARENA study. It's also what we've agreed for the existing policies for the 2016 Paris Accord. And then you've got the transforming energy scenario, which is if everyone got behind sustainability and really transformed our society beyond what we've already promised. So the PES is blue. The TES is yellow. The dotted line you see at the top of the graph is actually where we need to get to actually completely replace fossil fuels with our planned systems. And the gray is in each column is the systems we already have that we can use. So how many power stations are we talking about here? So according to the new energy split, if we were to actually make the number of power stations, the blue is in 8 years' time, are we really going to make so many new power stations? The yellow is what we would actually hope to do to really sort of transform things and get things moving along. And as you can see, these numbers are huge, and it's simply not really practical. We don't have the money, we don't have the time, and as it turns out, we don't have the resources as well. In conclusion, the additional system capacity, that number is incorrect. There should be 36,007. The same non-fossil fuel energy mix translates into, again, that is actually the old numbers. So the electrical power generated from wind and solar is highly intermittent. We will need a massive buffer storage. The total mass of lithium-ion batteries required to phase out fossil fuels is about 2.8 billion tonnes. Current thinking has seriously underestimated the scale of the task ahead. Nuclear is vital to keep the industry going, but it cannot be expanded to replace fossil fuels. It is not the magic bullet. Neither is biofuels. We will need biofuels in larger capacity than we have them now, but they cannot be the magic solution. Battery chemistries other than lithium-ion should be developed according to different mineral resources. There's a projected mineral shortage of supply for raw materials of battery manufacture. So 2019 production rates are not even close to being appropriate, but neither are the 2022 stated mineral reserves. So yes, we need to do a lot more exploration, but frankly, the task is so large that perhaps we should rethink the plan in the first place. Metals are the new oil. So metals of all kinds are about to become much more valuable, and an evolution of the industrial ecosystem is highly likely. There is a coming renaissance for the exploration for the mining of minerals. Thank you, Kitos and Aita. Do I say Aita? Yeah. Anyway, thank you.
Thank you, Simon. It's extremely interesting presentation. Audience, you have questions for clarification? No. You have? Okay.
I don't know, can you see me or not? But
I can see you, yes.
Great, great presentation. But my question is, I'm geographer by background, and my question concerns geography, new geography, because previously it was very easy to transport oil. But now the new solar panels especially, but also wind, which cannot be built anywhere, and it creates probably new places. So what kind of geography it is? Question of smaller cities and their role comparing with big metropolises.
So I've just done a straight calculation of our society the way it is. If we were to phase it into renewable power systems, what would that look like? If we were to go down that path, I don't think it's practical, for reasons that you were just alluding to, you simply cannot put up thousands of wind power stations. And solar power stations can't just go anywhere. And so on and so forth. Hydro power stations can't go just anywhere. So there are practical and logistical bottlenecks to this. So this study is to provide a theoretical limit, if you will, a task. So the practicalities of doing this are so enormous that the purpose of the work is to get people to stop assuming that everything is going to be easy and fine and the way things are now, and get to actually develop a new society that is fundamentally different to what we have at the moment. But the limitations are not just energy, not just money, but they're also raw materials, minerals, and metals as well. Right? And so if we were to completely construct a society with what we have, what would it look like? And geography is going to be front and center of how much of this is even possible. So your question's a good one. Follow it up with a study.
So next.
I have also one question about assumptions about technologies, because you did calculations and you started from 2018, and in your calculations up to 2050, what was assumption about the change in technologies? They remained fixed to 2018 level, or you at least assumed some kind of improvement in technologies?
So the 2018 numbers was for about the size of the system. How many cars are we talking about? How many cars, how many trucks, what distance did they travel?
No. My question is about the need of different kind of raw materials. And you calculated how many batteries are needed. And now my question is that, do you expect that technologies producing batteries will not change during 32 years?
So, yes, of course they will change. But to actually do this study, I have to make some assumptions. So what I've done is I've taken the market predictions from the IEA of what they believe the market will be in 2040 and in 2050. And so there's a whole series of theoretical systems like solid state batteries will be a big thing, but they're not commercially available yet. So this is the actual target to hit. Yes, human innovation will invent new things. For example, we don't have to make batteries out of lithium-ion chemistry at all. We could make it out of fluoride, like the fluoride in your toothpaste, or zinc, or sodium. And those minerals don't have these supply risks to them. But at the moment, we are focused only on lithium-ion batteries. And so the purpose of this work was to show that our fixation on lithium-ion battery chemistries is a shortfall. Is short-sighted. So what the future might come and in terms of innovation, when we get there, I assume it will be different to what this report is showing. But the purpose of this report is to get people thinking at least in the right direction.
So, thank you. Please.
Thank you for the interesting presentation. The numbers you showed, they're quite extreme, I'd say. So how do you feel? Is that doable? Do you have hope? Can we get it done?
Yes. So when I talk to my daughters, do I have hope for them? Yes, I do. But the system that we are working with at the moment is about to go through an evolution. And that evolution won't be that comfortable because we've left it so late. I do have hope with the caveat of saying we will not do it the way we think we're going to do it. We're not going to use lithium-ion chemistry. We're going to use lots of chemistries in parallel. What I also think is society will fundamentally change once it becomes apparent that we're off fossil fuels and we're onto the next system, which has less energy return on energy invested. So society and how it's structured and how we do things will fundamentally change. So I see this change as quite disruptive, but I also see it as the project of the century. The problem solvers in the technical problem solvers have so much to contribute to society now more than ever before, because we are required to get in there and make a new system. So the work we do will be actually quite valuable to society, and it'll be difficult, but I think we can do it. But change is coming. You can be part of the solution or you can be part of the precipitate.
Thank you. You have more questions? I not see. Once again, Simon, lot of thanks. We have a lot of materials about thinking today and future. Thank you. And finally, congratulations, Finland, it's world champion ice hockey.
Thank you.